You know, 5G feels like it just got here, but believe it or not, the race is already on for what's next. Today, we're going to dive deep into the absolutely mind-bending technology that's set to power our future, 6G. Let's unpack it.
So you might be asking yourself, do we really need anything more than 5G? Well, just think about the kind of world we're building. A world with truly immersive VR that feels real, holographic phone calls, and entire smart cities where every single car, traffic light, and sensor are all chattering away to each other in real time. The amount of data we need is just exploding, and 5G, as fast as it is, well, it's just not going to cut it.
To actually power that future, engineers are aiming for speeds of 1 terabit per second. Now that is not just a little step up, it's a monumental leap. We're talking roughly 100 times faster than the absolute peak speeds of 5G. And here's the problem. The technology we're using today, even the most advanced 5G stuff, just can't get us there. We've basically hit a physical wall.
So how in the world do you break through that wall? Well, you need a new road, a much bigger, wider, and way faster one. And that's where Terahertz technology comes in. The best way to think of it is as this vast, empty, multi-lane superhighway for data that's just been sitting there totally unused, waiting for us to figure out how to drive on it.
So what exactly are terahertz waves anyway? They live in this kind of sweet spot on the electromagnetic spectrum right between microwaves and infrared light. For decades, this whole area was known as the terahertz gap because, honestly, the signals were just incredibly difficult to create and to detect. But if you can crack this gap open, you unlock these enormous fresh blocks of bandwidth. And that is the secret ingredient for those terabit per second speeds. This is the very foundation of 6G. Of course, if this were easy, we would have been using it for years. This data superhighway is amazing in theory, but actually paving it? That's one of the biggest engineering challenges of our time. These super high frequencies come with some serious, and I mean serious, drawbacks.
Let's break down the 3 biggest villains in this story. First up is severe path loss. THZ waves lose their energy and just fade out incredibly quickly. It's like trying to shout in a hurricane. Second, they are extremely sensitive to being blocked. I mean, forget concrete walls. Your hand, a single piece of paper, even heavy rain can stop the signal dead in its tracks. And finally, there's this weird thing called the beam splitting effect. Because the signal is so wideband, the beam can literally split apart and go in different directions, which of course makes it way weaker.
To really put this into perspective, just look at how it compares to 5G's millimeter wave. And you know, 5G already felt kind of fragile, right? You walk behind a big pillar and your signal just tanks. Yeah, well, 6G's terahertz waves take that fragility to a completely different level. Even the air we breathe can absorb and weaken these signals. So the billion-dollar question is, how on earth do you build a reliable network with a signal that is this delicate?
Well, that is where the engineering genius really comes in. To tackle these massive problems, you need a whole new set of tools. So let's take a peek inside the toolbox that researchers are using right now to build the very first terahertz communication systems from the ground up.
You know, it really all boils down to 3 fundamental things. First, you need a source to actually generate the THC signal. Then, you need a detector to receive it on the other end. And finally, you need a modulation scheme, which is basically the language you use to stick all your digital ones and zeros onto that signal. Getting all 3 of these just right is absolutely mission critical.
And just to give you a quick taste of the complexity here, there isn't just one way to make a THC wave. Engineers are basically going down 2 main roads. There's the electronic approach, which uses really advanced semiconductors, and then there's the photonic approach, which uses light. We're talking high-powered quantum cascade lasers to create the signal. Each one has its own set of pros and cons when it comes to power, cost, and just sheer size.
And it's the same story when it comes to encoding the data. You have to make some serious trade-offs. You could go with a simpler single-carrier method, or you could use a more complex multi-carrier scheme like OFDM, which you might know from Wi-Fi and 5G. The multi-carrier way can cram in a lot more data, but, surprise, surprise, it's also more vulnerable to some of those pesky THC signal problems we talked about.
Okay, so we've seen the challenges, we've looked at the basic tools. Now for the really cool part. Let's see how engineers are putting these tools together to come up with these brilliant solutions that solve the whole terahertz puzzle, one piece at a time.
This quote just nails the first big problem perfectly. Remember that severe path loss? The signal is like a faint whisper in a storm. To get it to travel any real distance, you can't just send it out everywhere like a light bulb. You have to focus all of that energy into one spot, kind of like a laser pointer. And the solution is something called ultra-massive MIMO. Now, MIMO stands for multiple input, multiple output, and it's already a big part of 5G. But for 6G, we're going ultra-massive.
I'm talking about antenna arrays with hundreds, maybe even thousands of tiny little elements all working together. They basically act like a giant satellite dish, precisely focusing all the signal's energy into a single, superpowered pencil beam that can punch through that path loss and actually reach its destination.
All right, so ultramassive MIMO gives us a powerful focus beam. Problem solved, right? Ha, not quite. Remember that other nasty issue? That wideband signal can make the beam scatter and literally split apart, and a powerful beam isn't much use if it doesn't actually stay together.
So the solution here is this incredibly clever bit of signal processing called delay phase precoding. It sounds complex, but think of it this way. The transmitter adds these tiny, super precise time delays to different parts of the signal before it even gets sent out. These little delays act like a focusing lens, realigning all the different frequencies so they all travel in the exact same direction. And the result? One perfect unified beam that doesn't split apart. Problem solved.
Okay, one final huge challenge: blockage. What happens when someone just walks in front of the beam or a truck drives by? The solution here might just be the most futuristic thing of all: reconfigurable intelligent surfaces. Imagine painting a wall or a window with a special material that acts like a smart mirror. This surface can be programmed to catch an incoming THZ signal and then perfectly reflect it around an obstacle, steering it right towards the receiver. It literally creates a brand new path out of thin air when the direct one gets blocked. It's incredible.
So, you've got these massive antennas, super smart signal processing, and intelligent mirrors. This might all be starting to sound a lot like science fiction. But what's so amazing is that this is all moving from theory into reality right now.
The gears are already turning. I mean, way back in 2017, the IEEE released the very first standard for communication up in this frequency range. And today, right now, 3GPP, that's the group that standardizes all our cellular tech, like 5G, has officially started its study of terahertz for 6G. All of this is building toward what's being called IMT 2030, which is the official vision for the whole 6G world. This really isn't a what if anymore, it's a when.
So why does all this incredible engineering wizardry even matter? Well, because it's going to unlock a future that 5G can only dream about. We're talking about fully intelligent and autonomous systems, like fleets of self-driving cars and completely automated factories. We're talking ultra-scale services, connecting not just billions of devices, but trillions. And at its very core, as you can see, 6G is being designed from day one for a world where everything is seamlessly integrated with AI.
And that brings us to our final thought. We've spent this whole time focused on the how, but the ultimate question is really the what. All this incredible engineering we've seen is paving the way for a world where our digital and physical lives are just seamlessly connected with near-instant communication. A world where every object has a digital twin and intelligence is just all around us like the air we breathe. So I'll leave you with this to think about. When that world finally arrives, what happens next?